Hello, my name is Reagan Shield, and this is my final video exam. And this will be my presentation just demonstrating 10 different jump techniques and just methods that you can use to analyze data. First of which will be Graph Builder. So Graph Builder is extremely useful for analyzing data. It's great for creating visuals that make a lot of information really easy to understand. So in the business world, these are ideal when you're giving presentations. Using the graph builder, as you can see here, you can make a variety of different graphs with your data. To list a few, you can do scatter plots, smoother, which will kind of smooth your line. You can do line of fit and just fit a linear line on it, or see if a linear line would fit. Ellipse, contour plots, box plots, histograms, pie charts, mosaics, bar graphs. All of these up top are different options you can do, so there's more than just the ones I listed. But now to demonstrate, so under the graph builder and sample data, we're going to use car physical data. If you go graph builder, I'm going to take type of car over in the Y and gas tank size for the X, and then do the box plot. And as you can see here, all these center lines for each type of car will be the median. The box is created is the IQR, so the interquartile range, and then there are max and mins generated, which are 1.5 times your IQR. So any dots you see outside of these max and mins are outliers, which means they really don't fit the data very well. But in the business world, I mean, this is one way to compare gas tank sizes based on different size cars and to really just get an easy interpretation of that. Okay, next is the ANOVA test. So ANOVA test is analysis of variance, and they are typically used to test differences between two or more means. So that can be confusing because obviously it's analysis of variance, so aren't you analyzing the means? But it actually does make sense because it makes inferences about the means through the analyzing of the different variances. So it can be used in a variety of ways, but one example that we've talked about in class a lot would be pilots. So does their breakfast beverage of choice make any difference in reaction times? So you could say one group drinks coffee, one drinks orange juice, one drinks water. You can test and see the reaction times and group them, and then run the ANOVA test to see if there's actually a statistical difference. So the example we're going to use though is the popcorn. So if you go to Analyze, Fit Model, and you throw yield in the Y, we can do popcorn, oil amount, and batch, and do a full factorial macro down here. So it's not only going to have them by themselves, but it's going to multiply them by each factor. And when you run this test, it'll bring up our response yield and our analysis of variance. So you can see a p-value of 0.0025, meaning that there is actually a difference in between whether you use small, large, or medium, or different oils. Different combinations can lead to a greater batch yield. So you come down to the bottom to the prediction profiler. You can do desirability functions, and then maximize desirability, and it will tell you actually the best combination to produce the maximum amount of yield, which in this case would be gourmet popcorn, lots of oil, and a small batch. Thank you. Okay, next we're going to do the chi-squared test. So this is known as pretty much the goodness of fit test. So if we've come to expect a certain process or a certain event happens a certain amount of times, and we want to test whether or not our observed data actually matches what we've had come to expect, chi-squared test is what we'd want to use for that. So basically it's observed, which is the data we take in, versus theoretical versus what we think it should be. So to demonstrate an example of this chi-squared test, I'm going to use the pipeline safety data. And we can go Analyze, and fit model. Actually, no, we're going to go analyze distribution. And we're going to look at the type. And that'll generate this distribution, which will show us different gas leaks and what caused them. So we have rupture, other, not available, and leak. So I guess this isn't what caused leaks, this is what happened to the pipeline. And if we go here and test probabilities, it'll bring this up here, which will perform the chi-square test for us. So let's just say we expect that all four potential disruptions would be equal. We guess each one would happen 25% of the time. So we hit done, and what this test will tell us is actually no, that's not true at all. The p-value less than 0.001, so there is definitely a difference than what we would have expected at them all being equal at 25%. So after doing this, we could then go and run more tests and see which one is actually the major cause, and it's just good ways to test what you think you know and what you come to expect based on your data. Okay, next we have design of experiment. So essentially DOE is a systematic approach to determine the relationships between certain factors affecting the outcome of a certain process. So it's basically cause and effect. You're going to take a bunch of factors, which could be, let's say, 5 different ingredients for a cake, and you're not only seeing how significant each one of those ingredients is on the outcome, but you're also seeing the relationships between those factors and how those work together in order to create that desired outcome. So you could either maximize something, minimize it, set a target, and you build these experiments to help you determine what are the optimal ingredients. So our example we're going to do is popcorn. So we have brand, time, power, number popped, and total kernels. So we're going to say we want to have number popped as our, well, we'll do number popped and total kernels. And then we can do brand, time, and power. Full factorial in here, so we're not only going to see each one in the relationship, or each one affecting the outcome, but each one times another one. Run this and we'll get our results. So up top we have responses for numbers popped, and then we have responses for total kernels. You can see how significant each of the inputs is on affecting each here in parameter estimates. So your low probability is going to obviously show that it has some significance. And if you go here, it'll actually break it down for you. So the brand, time, and power plays the biggest role. Then it would just be brand, and then it works its way down. You can see in significance levels. But if you go to the very bottom, and the same thing will be here for total kernels, time and power play the largest role, then brand, time, power, brand, power. So obviously here you can see power is pretty important. And if you come down to the prediction profiler and you do maximize desirability, it will then take all three and give you the optimal levels in order to produce the most amount of popped and the most total kernels. So in this case it would be Wilbur. You'd want to cook these for 3.43 minutes and at a power level of 6.56. So this is extremely useful in the business scenario. If you want to focus on one aspect of making better popcorn, you can actually come up here and see which ones play the biggest, which ones influence the outcome the most, and go from there. Next we have time series models. So these are incredibly important when used in business. So you're basically going to take a bunch of data you have. These could be sales, could be production, and anything with a timestamp really, so it can be traced back through the past. You're actually going to plot all these points, and then you can do a lot of different things with that. One example is for Coca-Cola. So let's say you got 10 years of data with all your sales for every day, each month, every year. So you can plot all that, and using different data analyzation techniques, you can actually forecast out future periods, You can predict sales not only for years but for each month. You can look at seasonal data, you can do random walk, you can do a lot of different type of forecasting methods, but time series is very important in business. And for the example, so I pulled up our steel shipments. So we have the amount of shipments we've done every day, or I guess once a month, for a few years. So we go analyze, fit y by x, go date and steel shipments. So basically this is just going to put our date on the bottom, which is pretty normal for time series, and then you have steel shipments. And this is very basic, so you wouldn't really forecast with this data, but you can go and fit a line. Right off the bat, this tells you that steel shipments throughout the years and throughout the months have not stayed stationary. There is a trend to them. It has slowly been increasing. And you can see that down here with the p-value, 0.001 or less than 0.001, saying there actually is a difference between sales over time, and it is increasing. So you could take this data and look a little more into it. Obviously the data set isn't very large, so you wouldn't be able to pull that much more information out of it, but you can see how with companies who have a lot more data you could actually forecast, and it could be very beneficial. Next we have Pareto charts. They're typically used for analyzing data by interpreting their frequencies. So typically used to infer frequencies of problems or causes of problems in a process. So let's say you're manufacturing steel nails, and there was a variety of different things that could go wrong. The machine could break, user error, the vibration in the machines might be too much, a ton of different possibilities as to what could slow or just ruin your process. And what these charts will do is total them up by frequency, and the bars on the chart will represent the individual count for each problem, starting at the largest count going all the way down, and then the line on the chart will show the cumulative frequency. So just as a quick example, I have just failure jump data, which has different types: contamination, corrosion, doping, metallization, miscellaneous, oxide defects, and silicon defects. So as a plant operator, you're going to want to know what is the cause of failure more often than not. So with this, you could go to Analyze, Quality and Process, Pareto plot. Failure will go here. Your number of times will go in frequency, and this will generate our plot for us. And as you can see, contamination with 14 would be the #1 cause, going all the way down to the silicon defect at 1. And as the causes decrease, you can see the total increase. So these are very useful in a plant. They can really show you what your priorities need to be as far as reducing these problems. Next we have reliability / survival. So again, in business, this is very important. Whether you're creating a new product and you want it to last a certain period of time, or even you have a product and you want to figure out when it goes bad, or when, let's say, an engine will fail. This allows you to take in data that you obviously have censored at some point, meaning you've tested after a certain period of use. Is it still functioning? At what level is it functioning? And in some cases, you'll censor data a ton of times, or for, let's say, an engine, you'll check it every 100 hours, and this could go on for 10,000 hours. And every time you check it, you see, well, did it fail? Did it not fail? And you keep your data organized like that. So reliability and survival has a lot of different models you can do. You have the life distribution, fit life by X, occurrence analysis, degradation, reliability forecast. So you could actually go ahead and once you take your data, you can see, all right, this is when we expect it to fail. Reliability growth and reliability block diagram. They all serve their own purposes, specifically for what you're looking for. Most of these use sensor data. For example, the life distribution, it calculates time to event. So this could be time till failure or time till expiration. But yeah, censoring this data will be in some cases a 0 if you checked it and it didn't fail, a 1 if it did fail, or simply you could check and censor it and be like, all right, at this point, this is at what level we're at. So for our example, we're going to look at engine valve seat data from JUMP. You can go Analyze, Reliability, and Survival, and we are going to do Recurrence Analysis. So engine ID, we will put at the label. Age will be our event timestamp, which is typical for reliability and survival, and then cost. And it will generate this for us. So on the event plot, each dot you see will be when that failure happened, or when cost occurred in this example. So it might not be failure, but it could be repairs, it could be something, but they just have a baseline, okay, it costs this money at this point. So there's data from multiple different engines and multiple different testings of each one. So you can see when each engine costs the company money. So this is useful in determining, okay, which engines are going to cost us the most money, how early on. So you can go down here to the MCF plot, and this is how the cost has to do with it. So you can see as time goes on how much your expected cost will be at what rate. So at a 1.0, it's like, all right, whatever we paid initially, we're going to pay again at 1, and so on and so forth. Really useful, and in a lot of cases you can plot a ton of different mean cost MCFs for, let's say, one for each engine type, and you can see, all right, well, this one cost me more money early on, this one cost me money later on, and you can kind of compare and see which engine would be preferred. And that can be used for many other different examples. Next, we have control charts, which are extremely important in any manufacturing setting and really in a lot of other situations as well. But they allow you to monitor your process and let you know when it's in and out of control. Allows you to check your capability. So let's say you have a customer that needs a certain job to be done in a certain way. He needs X amount of parts in X amount of time at certain specifications. Having properly maintained control charts will tell you exactly what you are capable of and whether or not you can accept that customer. X-bar and S-charts are process average and standard deviation. X-bars R charts are range. NP charts will give you the number of defectives in that process, and then P charts would be the proportions of defects in that process. As a quick example, I have airport data, I have the day, and I have the number of delays on that day. So we go Analyze, Quality and Process Control Chart Builder, put the date down on the bottom, and delays, and this will allow you to see the amount of delays as the date progresses on the bottom. So first off, it gives you the average per day of delays, which would be this green line, and then if you go day by day, you can see how many were going on. It calculates a UCL and a LCL, so you can see on which days it's pretty much out of control, more than typical. And these UCL and LCLs are going to change. They're going to be basically go with the moving average essentially. And then down below it gives you the range for these delays as well. So there's a ton of different charts you can do. This is just one example, and this isn't manufacturing, this is just delays. But it's a good way to see if you're operating typical to what you normally do, or if for some reason for a month you're all up here out of control. Clearly something is going on in that month that is causing that, and you need to go and analyze and take care of that. Hypothesis testing is next. It is essentially the backbone of statistics. At any point, you're typically trying to disprove a null hypothesis, allowing you to prove significance. It's used in many different tests and models throughout statistics as a whole, but just a few examples or a few calculators we have on our JUMP software would be hypothesis tests for one mean, one proportion, two means, and two proportions. So essentially you can test if one mean is significant compared to what you think it is, or if you have a certain group of data and you expect that, okay, 10 of these are going to be bad, and you want to know if 15 are bad, is that significant or not, or is that really too close to call, and there wouldn't be any statistical difference. So it allows you to test the results of your experiment or survey and decide if they are meaningful or not. Without running the test, your experiment and survey data is all pretty much useless unless you can prove it statistically. So just one example, I pulled up a hypothesis test here. So this is just the summary data. Didn't have a data set for this, so I'm just going to do this. So let's say you have two different means and you want to know if statistically they're different. And there's a lot of different factors that go into this, including your sample size, the population the sample's taken from, and whatever significance level you want. So let's say we want to see if two sample means are statistically any different. So let's say the first one is 500. Sample or population standard deviation of 25. Well, actually, let's do 50. We'll say this sample size was 1,000. Sample 2 mean, we will do 450. Standard deviation of, we'll do 35. Sample size, we'll do the same at 1,000. And right away, it'll calculate whether or not they are different. Immediately, it gives us a p-value of less than 0.001. Lastly, we have the mosaic interpretation. So mosaic plots are a graphical method to interpret data from at least two qualitative variables. You need a minimum of two, however, you can have as many as you'd like, and the mosaic can be as large as you would like. One example, if you have a group of 5,000 college students and you want to break down visually how many are male and female, how many are over under 5'8", and how many have blue or brown eyes or another color. You can put all this into a mosaic and it will give you a really nice graphic on the differences between each. So one popular example is the Titanic example. So I have the data here. We can go to Graph Builder. And then we can do survived down here, so whether or not they survived. Then we can do, actually we'll do survived on the Y. Then we'll do which class they were in. And if you go over here to the mosaic, so now you can see survived, red will be yes, blue will be no for each class. So first class, a lot more people survive. Second class, less. Third class, even fewer. And then by the width, you can tell how many were in each class. So there was definitely a lot less first classers than third, but there was even less second than first. And this is just from the data we have, so it might not be actually representative of how many, but you get the point. And then you could actually go a step further and throw in sex, and it'll break it down, and you'll have two side by side, so you can have females. First class females, almost all of them lived. Still follows the same trend down to third class. And then for males, a lot more died because they put the females on lifeboats and did not do the males. So again, just a good graphical interpretation of who lived and who didn't and how that breaks down. These can be applied in business. Great for meetings, great for just showing what could be complicated data in a very simple way. And that concludes my final presentation. Thank you for watching.